Today's inverted lecture is going to be about polarity and how that affects solubility and other physical properties. So let's briefly review electronegativity. En, this is the ability of an atom to attract electrons towards itself within a bond. And so we had mentioned before, A and B are two bonded atoms, and the shared electrons between them may be pulled towards one atom or the other. The Pauling electronegativity table is shown here, and the different values represent electronegativities ranging from 0.7 to 4.0. You will have this on an exam, so you don't need to memorize values. Remember that electronegativity increases up and to the right. We have three types of bonds in this section. Nonpolar covalent. So when you subtract the electronegativity of two atoms, if it's less than 0.5, it is this category. An example is a CH bond. Carbon is 2.5, H is 2.1, and when you subtract them, it is 0.4. If you have the same thing bonded to each other, you have the same situation. Okay, nonpolar covalent. If the electronegativity is between 0.5 and 1.9, this is called polar covalent. And an example will be shown on the next page. And then if one atom is way more electronegative than the other, and the difference is greater than 1.9, it's ionic. So fluorine is so electronegative, it takes the electrons away from lithium and has them both. So this delta En is 3.0. Organic compounds contain all different types of bonds. So let's look more closely at the polar covalent bond. In this case, remember that the delta En is 0.5 to 1.9. When you find that is the case, such as a carbon-chlorine bond, you can draw a dipole that results due to this difference in electronegativity. And the dipole always points towards the more electronegative element, which is chlorine in this case. That develops a partial minus charge on chlorine and a partial positive charge on carbon. We're not going to worry about this too much, but the units of dipole moment are known as Debye. Okay. And so what I have shown here is a bond dipole. The sum of all the bond dipoles across a whole molecule tell you whether that whole molecule has a dipole or not. And that will determine whether our molecule is polar or nonpolar. Okay? And so we're going to follow these rules when we're determining that. First off, you must have the Vesper geometry. And so remember, a carbon that has 4 bonds would be tetrahedral in an sp3 geometry, and that is shown here. Draw all bond dipoles if delta En is 0.5 to 1.9, which it is for carbon-chlorine, but not for CH, so there is no dipole here. Sum all of your dipoles as if they were vectors, and so they all have a component that's pointing to the right, and you have a net dipole. If you have a net dipole, your molecule is polar. In this case, we just added one more chlorine, which adds a new dipole. If all of your dipoles are out, or if all of your dipole arrows point in, they're going to cancel and you will have no net dipole, and in this case your molecule is nonpolar. Then there are cases in between where you may only have 1 or 2 dipoles. So in this case we have an alkene with 2 bromines off of the alkene. If we draw the dipoles, we can see that the net dipole arrow points towards the right. This is the cis alkene, so I have drawn here cis, and it is polar. If you draw the trans, you will see that there is no dipole and it is nonpolar. We also have to consider lone pairs, such as with ammonia. There is a small dipole due to the lone pair. Remember that nitrogen in this geometry is called trigonal pyramidal, and so these arrows all add to the up direction. One last aspect is the s character of an orbital, and that is more electronegative if you have more s character. So sp is the most electronegative hybrid orbital, and it has 50% s. And the way to get this is to add the superscripts and see what percentage of S is of those superscripts. So in this case for sp2, S is 1/3 or 33%. So here is a summary chart in which it shows some net dipole moments for molecules, and some will not surprise you, such as H2. We would expect this not to have a net dipole, but some, like CO2, may surprise you. So in these cases, take the time to draw the Lewis structure for CO2. Remember that you count the valence electrons, so 4 plus 6 times 2 equals 16 electrons. Once you add all bonds and lone pairs, you see that this is the structure. You have to have the Vesper geometry though, so you have to look at your Lewis and convert it to Vesper. The carbon has 2 bonding areas, which is sp, and so sp is linear, and so your Vesper is the same as the Lewis structure in this case. You ask yourself, do I have polar bonds? So yes, I do in this case. OC bonds have a delta En of 1.0, which means you have 2 dipole arrows pointing towards oxygen. In this case, you add the vectors and they cancel. So you have no net dipole because the vectors cancel. Therefore, the molecule is nonpolar and has a 0 net dipole moment. Now that we understand about polar bonds, we can understand better about attractive forces that occur between molecules. So interactions occur between molecules in a sample. And over the whole sample, these are going to add up. So when 2 molecules bump into each other, the small attractive forces are what we're describing. And these result in melting and boiling points, density, and solubility, for example. Ionic compounds have very strong ion-ion forces between the cation and anion. And so they are hard to break, these forces, and they tend to be solids with high melting points. On the other hand, covalent compounds have a variety of different types of intermolecular forces that can occur. And so intermolecular forces are forces between molecules, shortened as IMF, and you may have also heard van der Waals forces. Because these vary, covalent compounds can be solids, liquids, or gases. And so these are the 5 types here, and we will describe the first 3 types in detail on the next few slides. And so let me briefly tell you about ion dipole and induced dipole. Both of these cases have induced aspects, and so if an ion is near a nonpolar compound, it can induce a dipole in that compound. And the alternative is if a polar compound is near a nonpolar compound, it can induce a dipole. An example of a polar compound from the previous slides was CH3Cl, and a nonpolar molecule, which we saw, was CO2. So if these 2 bumped into each other, we would have an induced dipole situation. Intermolecular forces are very important in terms of the properties that are observed, and water is a great example. Water is a small molecule that you would expect to have a relatively low boiling point, and it would be expected to be negative 80 degrees Celsius. So we would not even be able to exist because it would only be gaseous. However, due to hydrogen bonding, which is one of the forces we're going to learn, the actual boiling point of water is 100 degrees Celsius. So now we're going to talk about these 3 intermolecular forces. So we're going to start with dipole-dipole forces. So dipole-dipole forces occur only in polar molecules, meaning that you must have a net dipole. And so here is CH3Cl shown with its bond dipole. And remember, the bond dipole in this case is also the net dipole because you want to sum all of the bond dipoles. We ignore CH bonds because remember, CH bonds are nonpolar. Okay? So if we had a solution of CH3Cl, the molecules could temporarily align as such, which kind of looks like this situation, plus minus, plus minus, plus minus. And so this is attractive forces and this is favorable, and even though they're small forces, they add up over the sample. Okay? So if you want to boil this as a liquid and convert it to a gas, so liquid to gas, you need to disrupt these forces in between the molecule. So it's important to know you're not breaking bonds, but you're disrupting these forces to be able to boil. And again, just a reminder that you do not want to talk about these forces until you draw the Vesper structure and understand whether you're going to have these forces or not. So CO2 is nonpolar, so it has no dipole-dipole forces. Ammonia is polar, and we saw that on a previous slide, so yes, it will have dipole-dipole forces. A special dipole-dipole force is a hydrogen bond. Okay, and it's kind of a funny name because it's not a bond, it's an interaction, and it's shown here with these pink dots, okay, and it's highlighted here. A hydrogen bond is an interaction, and it's due to a strong dipole between an OH bond. So this strong dipole allows lone pair nearby to associate with that, and see you're matching your charges here. So the partial minus due to the lone pair wants to be near the partial positive. And this also occurs in DNA between the base pairs. And here's an example. Okay. So looking at hydrogen bonding, you have to have an NH or an OH, and you also have to have lone pairs on oxygens and nitrogens to be able to do hydrogen bonding. Okay. So here are two practice problems in which we want to explain the difference in boiling points. And so in the first problem, we have an alcohol. In the second part, we have an ether. Okay, and these are both constitutional isomers of C2H6O. One has a high boiling point and the other does not. And so in this case, the high boiling point can be reasoned because the alcohol can hydrogen bond, but the ether cannot. If we take the time to draw out the ether, we'll see that we have CH bonds, but we have no OH bonds. We have a lone pair on the oxygen, but that is not enough. You need to have NH or OH as well. Okay? And here's the bond line formula for the ether. So ethers cannot hydrogen bond with themselves. The second problem compares an OH group, an alcohol, with an amine. The molecular weights, again, are pretty similar, so we can't reason that. The boiling point, however, the alcohol is higher than the amine. If we take the time to draw out the OH and NH bonds, we can see that the delta electronegativity is 1.4 for an OH, but delta EN for an NH is 0.9. So in the end, we have a stronger dipole on the OH bond than the NH bond, and that stronger dipole means that you have a stronger hydrogen bonding interaction.